Okay, I'm picking up in the 2.1 notes. It is Monday, October 11th. We just finished multiplying out x plus delta x cubed. And I got x cubed plus 3x squared delta x. Think of the delta x as just like another variable. Plus 3x delta x squared plus delta x cubed. Okay. Here I would get 2x plus 2 delta x. Here I would get minus x cubed minus 2x. And again, I stress the importance of when you're subtracting f of x to subtract the entire function and putting that in parentheses. All over delta x. Okay, that was a lot of algebra. But here's where the fun part, things start to kind of canceling out, or kind of dropping out. So I notice I have an x cubed here and a minus x cubed here. Those have a total of 0. I have a 2x and a negative 2x. That would be 0. And then I'm left with a little simpler expression here of having 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. Okay. Everybody with me? So now I'm like thinking, when can I direct substitute 0 in for delta x? And I can't yet because I have a delta x in my denominator. I'd be divided by 0. But does anyone see something we could do up top in order to maybe get the delta x's to cancel so we can direct substitute? What just happened there? I notice they all have a delta x. I could factor that out. Okay. Factor that out. So I would be left with, in my first term, just 3x squared. In my second term, I would be left with 3x delta x, because there's 2 of them in that term. Only factor 1 out. Plus, there's 3 in the delta x cubed, that'd be delta x squared. And then factoring out the delta x from the 2 delta x, I'd just be left with 2. Again, just think of it like another variable. Then these finally cancel. Now that I have common factors. And then I'll go ahead in the next step. Now I can do the direct substitute with plugging 0 in for delta x. So I end up getting 3x squared plus 3x times 0 plus 0 squared plus 2. So you end up with the final answer of 3x squared plus 2, because those are obviously just 0. And this is my f prime of x, which that stands for, that is the derivative. So that is the equation that would give me all of the slopes at every single x value of this equation. All of the slopes of the tangent lines at every single point. So remember, your derivative, it's a function, it's an equation, it's a slope equation. Okay? They didn't ask me to find the derivative at a specific point. They asked me to find the actual derivative, and the derivative is a function. So that's why we got something out with x's, right? One thing you can notice, because we started off with the polynomial function, what degree polynomial function is this? Yep, you can see it. 3. He's like, show me 3. Okay, what degree polynomial function is this one? 2. Okay. Started with 3, went down to 2. All right, let's try another one. Find the derivative of f of x, which in this case I have 2x squared minus x by the limit process. All right, I'm going to throw a different notation at you this time. Instead of finding f prime of x, let's find dy dx. And that's the same thing. Since we want the actual derivative equation, we're going to take the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's your limit notation for the derivative equation. Okay, I'm not using the one with c's. That'd be if I wanted a specific point. Okay, so let's go ahead and apply this definition to my function here. So I have the limit as delta x approaches 0. F of x plus delta x, that means I'm plugging that in to my function in for x. It would be 2x squared minus x. And you're plugging in x plus delta x. Minus f of x. F of x is 2x squared minus x. Don't forget your parentheses there. All over delta x. Okay. Make sense where I'm plugging everything in? Now the fun algebraic part where you just get to simplify this. That's the best part about calculus is there's so much like tough algebra that's really fun and satisfying to simplify. All right, here obviously I have to square this first, so I'd get x squared plus 2x delta x. We just did that plus delta x squared. And then I'll distribute the 2 in my next step here. All I did was I squared that. Here I get minus x minus delta x minus 2x squared plus x. Okay. Next order of business, I'd have to distribute that 2 through. I get 2x squared plus 4x delta x plus 2 delta x squared. I already see a negative x and an x. And guys, this should like happen. A lot of things should kind of cancel out if you're doing this process right. And then I saw that minus delta x minus 2x squared all over delta x. What else cancels in my numerator now at this point?
2x squared.
Yeah, the 2x squared. Thanks, Mark. 2x squared cancel out. In my numerator, I'm going to do this in one step. In my numerator, am I left with something that I can factor out delta x, or am I left with something that every factor has a delta x? I am, so I can go ahead and factor that out. So I would have, factoring out this delta x, I would have 4x plus 2 delta x minus 1. And then those cancel. And then I can go ahead and plug in 0 for delta x. And we get 4x minus 1. I am recording this, too, Delaney. And that would be my dy dx. That would be my derivative. So basically, guys, and this is a good example, because we know what this graph looks like. 2x squared minus x. Now, I don't know exactly what it looks like, but I know, let's see. I know it's a happy face, and I know it's like vertically stretched out. I don't know. I'm just going to draw a sketch like this. Just really rough sketch. Okay. That's my original equation. Some parabola that's opening up. My derivative gives me the slope at all of the tangent lines. So this 4x minus 1, this slope equation, if I want to figure out like what the slope was, let's say this point is 3. If I want to figure out what the slope is, I could plug 3 in here, and that would tell me exactly what the slope of the tangent line is at that point. Okay, if I want to figure out, hey, what's the slope here when x is 0? I could plug 0 in here, 4 times 0 minus 1. Oh, your slope is negative 1. It would tell you exactly what the slope of the tangent line is. We just get an equation to represent the slope at every single point on our graph. Okay, we get a function for that. And this one started off degree 2, its derivative, degree 1. Okay, so I see a little pattern so far. In the last example, I had a degree 3 polynomial function. My derivative was degree 2, was 1 degree less. Here, degree 2, my derivative was 1 degree less. That pattern will always hold true for polynomials. The derivative will always be 1 degree less, okay? And we'll look at some graphs too and explain why you get a linear derivative for a quadratic. Okay, we're going to try one that's not a polynomial. And I'll show you some things in your graphing calculator too also. I think we'll fix that. I guess I can keep the recording rolling. So this time I have my square root of x. Okay, they want me to find dy dx. That's another notation I need to recognize. Hey, that means they want me to find my derivative. My slope equation for this square root function. Then they're asking me, what is the slope of the curve at the point 4, 2? All right, let's just start by finding dy dx. So that's the derivative of y with respect to x. That's kind of what that means. I just read it out loud as dy dx. So that means I'm going to keep writing this down because the more you write it down, the easier it's going to be to memorize it. I'm going to take the limit as delta x approaches infinity of f of x plus delta x minus f of x all over delta x. Okay. So this piece right here, I need to plug in x plus delta x into my function. So I get the square root of x plus delta x minus f of x. Well, f of x is just the square root of x. So I don't really need parentheses for this one because it's just one term. So I'm just going to write it like this. All over delta x. All right, now here, there's no like distributing, there's no like simplifying I can really do in my numerator. I obviously can't subtract these, they don't have the same radicand. So you have to use some of our limit strategies that we learned in chapter 1. And one of my limit strategies that I did with radicals was I often multiplied by like the conjugate. Okay, even if it was in the numerator. I'm not trying to rationalize it now, it's just one of my limit strategies. So I see this in my numerator, I'm thinking, all right, maybe if I multiply by the conjugate, which would be the same terms, but plus instead of minus. If I multiply the top and the bottom by the conjugate, this might simplify my limit a little bit so I can direct substitute in 0. Okay, so this is where chapter 1 comes into play and knowing your limit strategies here. Okay. This is just part A. So, when I multiply these, I can just multiply the firsts, and that's x plus delta x. The radicals just cancel each other out. The outer and inner are going to total 0, so you don't even need to do that. We talked about skipping that step in your head. And then I can just multiply the last, so minus the square root of x times the square root of x is x. Oops, on bottom I got to actually do the conjugate yet. So on bottom, don't try to multiply that through. Just leave it as delta x times that conjugate. Okay. Everybody good with that step? Nothing really technically new. My numerators. Hey, I have x minus x. And again, with this method of finding derivatives using limits, this happens a lot, where stuff in your numerator should kind of start dropping out. Okay. So now, just for sake of saving, I don't want to rewrite this again, but now I have delta x over delta x times this conjugate. So these would cancel because you have 1 over 1. So that all simplifies to 1 over the square root of x plus delta x plus the square root of x. And now I'm good to go ahead and do my direct substitution here. And I'm getting 1 over the square root of x plus 0 plus the square root of x. That gives me 2 root x's. And that's my derivative. Remember, it's okay to leave radicals in the denominator in calculus. There's my slope equation. Now, for sake of what I was just talking about with polynomials, I know this technically isn't a polynomial function, but the square root of x is x to what power? Go ahead. 1/2, right? This is the same as x to the 1/2 power. This right here, I have x to the 1/2 in my denominator, which is really the same as x to the negative 1/2. So I still kind of like dropped a degree, if you will. Before I went from x cubed to x squared, where I subtracted 1 power, here 1/2 minus 1, negative 1/2. So that pattern still technically fits, even though this isn't a polynomial. Okay, and that's what the next lesson will make those connections clearer. Okay, so there's my answer to part A. That's my slope equation. So part B says, well then what's your slope at the point 4, 2? So they're really asking for the slope of the tangent line at x equals 4, and I'm not going to really worry about the 2 for right now, because in my slope equation, all I need to do is plug in x, right? There's no spot for me to plug in y. So I can take my derivative, my slope equation. If I want to figure out, hey, what's the slope of the tangent line at x equals 4, I can just plug 4 in for x, and that I would get 1/4. So the slope at that point, the instantaneous rate of change is another way to phrase that, at the point 4, 2 would be 1/4. And again, we know what this curve looks like. Let's see if that kind of makes sense. We have this square root curve that goes like this. We have that point 4, 2. So we just found this equation would give us the slope at every single point. So at the point 4, 2, if I were to draw this tangent line, it looks pretty flat. It's definitely a positive slope, so it kind of makes sense that that would have a slope of 1/4, right? It's pretty flat there. Okay. What do we got next here? Okay, taking it one step further. And again, folks, remember these things, because it's a Monday, these things all mean the same thing. The slope at a point, the slope of the tangent line at the point, they're talking about the same thing. Instantaneous rate of change, derivative at a point. Those all are talking about our derivative. Okay, this time, they said, find the equation of the tangent line. So they're not necessarily asking us to find like our slope equation, our derivative. They want us to actually find that linear equation of the tangent line. Now, tangent lines are obviously always linear, okay? So if I were to look at this last example here, they don't want me to, we will need to find the slope equation, but they want me to find the equation of this line right here. So this line would obviously be like y equals 1/4 x something, because we know the slope is 1/4. They want me to find this equation of that line. So there's two things you need to find when you're writing an equation of a line. You need to find the slope, And you need to find like the y-intercept if you want to do y equals mx plus b. But we're going to do point slope form because in calculus, you can just leave your answer in point slope form. You don't even have to rewrite it in slope intercept form. So really the two things you need to write an equation of a tangent line is the slope of the tangent line, and we need a point. And our point right now is 2 something, but we could figure out what that point is obviously by plugging 2 into our equation here. So we get 1. Okay, so we have our point. We want to find it at the point 2, 1. And maybe they'll give you the point. Like in the last example, they said, hey, find it at 4, 2. And maybe they will, but here they didn't. They just said at x equals 2. But we know obviously that's the point 2, 1. We can just figure that out. So now we need the slope of the tangent line at 2. All right, there's 2 ways you could do this. We could do this whole process like we just did. And in the end, we could just plug in 2 for x. Or, and this is why there's an alternative definition, the easier way to do it is to use this alternative definition for our derivative when they give us a specific point. Hey, if we want to know the derivative at a specific point, we can plug in the point within our process, and it makes the algebra a lot less hectic, okay? But if you didn't recognize that, or if you didn't want to memorize the second definition, you could totally use this process and it would work that we've been practicing. You find the derivative equation, find the slope equation, and then end by plugging in that point, just like we did in this example. All right, and I'm going to walk you through this alternative definition because if you recognize this, hey, I want to find the slope at a specific point, this process goes a lot quicker. So here's that alternative definition. I'm just going to copy it down right here. It's the limit as x approaches that value of f of x minus f of c all over x minus c. Okay, so this notation and your number here, your point, think of that as your c. We want to find f prime of 2. What that means is we want to find the derivative or the slope at 2. Okay? Normally you write f prime of x. That means the derivative at every single point. This is specifically at 2 is what that notation means. Okay, so watch how this is just a little bit less algebra. So we want to find the limit as x approaches c, which is 2, of f of x. So my equation is 1 over x minus 1 minus f of c, and c is 2. All over x minus c, which is 2. All right, here, we know what f of 2 is. We found that over here. F of 2 is 1. I swear I didn't touch it. F of 2 is 1, so it's basically asking you for the output. So we know that's 1. I'm just going to write that up here. All right. I see a complex fraction here. A fraction within a fraction. So my first kind of strategy to try to simplify this is to try to get my numerator to be one fraction, then perhaps like times by reciprocal. So if I have 1 over x minus 1 minus 1, I'm going to write that with common denominators. At this point, with all this algebra, is a good time for my spiel of a lot of students understand the calculus concepts. They understand what they're doing here, but they struggle with the algebra. Okay, that's why algebra is important. So then my numerator, so I have common denominators, so I just rewrote 1 as x minus 1 over x minus 1. I have 1 minus x plus 1. So those 1's end up canceling out. So you're going to have 1 plus 1. So I have a negative x over x minus 1 all over x minus 2. Oh, no, those x's don't. Sorry, those 1's don't cancel out. We get plus 2. 1 plus 1. Sorry. I think I just checked my answer key. 1 plus 1 is not 0. Okay. You're subtracting this all. So I have negative x plus 1 Maybe I should have taken 2 steps. Okay. Phew. Good catch. Everything else looking good. Now I can times by reciprocal. So that'd be 1 over x minus 2. All right. Now these are looking really similar. I have negative x plus 2 and x minus 2. Anyone know what I could maybe do here in order to make this like an x minus 2 or like a little algebraic?
Factor out -1.
Good job. Yep, factor out a -1. It's not really a trick, it's more a strategy. Good job, Jason. And then these guys cancel. Remember, you can always cancel factors and numerators and denominators with rational fractions. So now I'm here. -1 over x minus 1, and then I can go ahead and do my direct substitution with 2. So now I'm getting -1. So that might feel like it wasn't that much less algebra than what we were doing, but it is a lot easier when you don't have to deal with like all the delta x's, the change in x's. By like plugging in that value kind of like within the limit process, it does make it a little bit shorter. All right, so now I know my slope at 2 is -1. And I know my point is 2, 1. So this is enough to write the equation. So here's my equation. I'm going to use point slope form. Y minus y1 equals m x minus x1. So the equation of the tangent line. Okay. x1, y1, that's my point. So I have the point 2, 1. And the slope is -1. And the AP exam lets you just leave your answer like that. You don't have to go any further. You don't have to put it in slope-intercept form. You can if you want to, but you don't have to. The only reason I would, if this is like a graphing active problem and you wanted to graph the line on top of that to make sure like it looks like it would be the tangent line at x equals 2, that would be the only case where I would do that. Let's do that really quick, actually. Let's take out our graphers. So this one's not hard to put in slope-intercept form. -x plus 3. That's what that equation would be in slope-intercept form. Let's go ahead and take out our graphing calculators. And go ahead, put in for f or for y1, you can put in the 1 over x minus 1. Which we know that's a rational function, so it should make a hyperbola. Okay, I don't know what my windows are at, but that looks good. Okay, so now in my y2, I'm going to put in that equation we got for that tangent line, which this is the only reason why you'd have to put it in slope-intercept form, -x plus 3. When I go to graph it, it should look like it is tangent to that point, 2, 1, and it looks like it is. Okay?
What did you do as your window?
I'm sure it's probably just -10 to 10 knowing me. Yep, -10 to 10 for both. Now, there's a program on your calculator that lets you calculate the tangent line at any point, and I'm going to show it to you, but it's illegal to do on the AP exam. But a problem like this, you wouldn't get your calculator for because of that program, right? So you'd have to like do all this math without a calculator, which we just did. But I'm going to show it to you as a way for just like conceptual understanding of like, okay, yeah, I'm doing this right, this process, even like when you're taking your test to like follow along. Okay, these problems are fun. So I basically just kind of added on steps, you guys. We just started off, well, actually, before I even taught you really what the derivative was, we found the slope of the tangent line. And now we're kind of just adding on how that's connected to derivatives. Okay, our derivative is our slope equation at any single point we want. We could use it to find the slope of the tangent line at any point, and now we're actually taking it a step further and writing these equations of the tangent line. We're going to do one more like this together. These are really common problems. Okay, find the equation of the tangent line at x equals 1. So 2 things if I want to find the equation of a line. First, I need the slope. So I need to find f prime of -1, the slope at 1. And the second thing I need is the point, which I know it's -1 comma something. So I usually do the easy one first. I'm like, okay, what is that point? I plug in -1, and I get 3. So they want us to find the slope of the tangent line at the point -1, 3. So that means the slope, you don't have to write this down, but. Okay, let's find the slope. So since it's at a point, I'm going to use this alternative definition. This one's easy to memorize too, because it's literally, guys, it's literally just almost like your average rate of change. We have f of x minus f of c all over x minus c. But you're finding the averages from the function to that point as our function is approaching that point, right? This is why this alternative definition does really come in handy, because it's very similar to your slope equation. F of b minus f of a all over b minus a, y2 minus y1 all over x1 minus x2. And then we're just using limits to say, okay, as my function is approaching that value, what is the slope approaching? That's where this comes from. All right, so we're doing at the point -1. And think about it, this is an equation, so we're kind of like plugging in -1 into our slope equation before we're even finding the equation, the derivative. Okay, f of x is x squared plus 2 minus f of c. Just going to go ahead and plug in 3 right away. F of c is 3. That's what we just found over here, f of -1. All over x minus c. All right, so I get x squared minus 1 over x plus 1. I can't direct substitute in -1 for x. So I'm thinking of some limit strategies, and I see my numerator is factorable. Difference of squares. Nice. That factors into x plus 1, x minus 1. The x plus 1's cancel. And now I'm just going to go ahead and direct substitute right away. I get -1 minus 1. All right. My slope of the tangent line at -1 is -2. Now I know the slope, and I know the point slope form. And I had this argument with an algebra teacher before. They were like, I don't teach point slope form. It's too much for them to memorize. I just teach them plug in x, y, and like solve for b, and then you can write your equation. I was like, Yeah, that's great. That's definitely works. However, they need to know point slope form. In calculus, we use it all the time. So I always like to try and incorporate it as much as I can in algebra 1 and algebra 2. All right, so oops. All we gotta do then is plug in our point, which is 3 for y1, -1 for x1, -2 for our slope. And again, you just get to leave it like that. Okay. I'm going to say this one more time. Could we have used our derivative definition, this one, to find the slope equation and then plugged in -1 in the end? Yes, we can do it that way. I'm just telling you, that process can kind of get hairy. If you make one small mistake with your negatives or your algebra, you're going to get the wrong slope equation. So using this alternative definition, like in this example, is way, way quicker. Okay. Perfect. I'm going to show you that feature in your graphing calculator now. So there's a couple like this on your homework. Given x squared plus 2, which that was the one we just did, x squared plus 2, add x equals -1. We just did that. Find an equation of the tangent line to the graph at the given point. All right, so we said that was y minus 3 equals -2, x plus 1. This is just the last example we did. Okay. Use a graphing calculator to graph the function and its tangent line, and then use the tangent feature to confirm your results. So you do have to put this in a slope-intercept form quick. Okay. So we want to graph that x squared plus 2 and the tangent line, just like we did in the last one. X squared plus 2, -2x, plus 1. Okay. So at the point -1, 3, that does look like that tangent line would fit my curve at that point. Okay. All right, here's the program. You're going to hit second, and then you're going to hit the program button. So we're really going to pick the draw option. So hit second, draw. And if you see number 5 says tangent, our calculator can draw tangent lines. And then what you can do is you can type in -1. It'll like pull up this x equals window if you just start typing -1. So it said, okay, where do you want me to draw the tangent line? At x equals -1, you hit enter. Okay, you can see it just traced over in blue. And it even gives you the equation of the tangent line, -2x plus 1, which we just found on our own without our graphing calculators. But this is a good way to like confirm your results. Like, hey, here's my function. Let me at first just even graph my tangent line. Does it look like it's tangent at that point? And then you can use this feature to test it. You guys want me to show you one more? Okay, let's do the one we just did. The 1 over x minus 1. The tangent line was -x. Well, let's not even graph our tangent line. Let's just graph the derivative. Just the function. Okay. So there's my function. We're going to hit second program. So it hits draw. We want to draw in a tangent line. So you hit 5. It should look like this. And then you're going to type in your x coordinate. So this one was at x equals 2. So you just type in 2. And again, it should kind of zoom up this window at x equals 2. Hit enter. It'll draw in your tangent line. And it comes up with the equation. Now here's where you're smarter than your calculator. Your calculator can't find exact values. So we found that equation as the slope was exactly -1 plus exactly 3, and we, using limits are correct, your calculator can't find exact limits. So what your calculator does is it only plugs in points really, really close to the value, like we used to do with vertical asymptotes. Like we would plug in, and I think your calculator does it to the point. I don't know if it's true. It's either 0.0000, like 4 or 5 zeros. I don't remember which one it does, but it can't calculate exact limits. So that's just a good, again, confirmation of, okay, we found negative x plus 3. Our answer is exact. Our calculator is rounded. So that's just to kind of confirm your results. Okay. This is a good place to stop in our notes. So we'll finish up this lesson tomorrow. Make sure you are doing some of the homework problems. So now that you have the outline and everything, try some of these limit ones. Oh, I gotta stop the recording.